Hi guys, today we're going to be doing the AtCoder beginner contest. This is the it's not the 175th, I guess, because the numbers start weird, but it's the contest 175. So yeah, we'll be doing that. It is slightly earlier than contests usually are, which means I'll be a bit more disoriented, but it's not that terrible. And yeah, that'll be it. This little TV thing in the corner is supposed to tell me when it begins and how long the contest has left, but I just can't, like it's barely visible. I don't know why this happens. Maybe it's a setting or something, but I just can't see it. Anyway, it doesn't really matter. Okay. Find the maximum number of consecutive rainy days in this period. I don't think any commentary is necessary for this because it's just straight up do what the problem tells you to do. Okay. This may be a more caseworky way to do that, but I mean, whatever, it's not that necessary. Okay. So, C into N. If we sort the array, then we can, essentially to make a triangle, we have to make it so the shortest two lengths, the sum of the shortest two lengths is greater than the third. So if we sort it, then we know that the shortest two lengths are going to be before j I plus 1 and k j plus 1, and if ai plus aj is greater than ak, then just count it as a triple. Seven. What? Oh, they have to all be different. So, and we don't have to compare AI and AK because we know they're sorted, so AJ will be in the middle. Yeah, I did not read that right. 8 and 39. They have this nice sample to catch the runtime errors, I guess. I guess this means D, but I mean, it's pretty clear from the statement that that's what it means, so this is probably just a typo. So, okay. C into, let's just call it NK. Yeah. Then it doesn't matter which side of the number line we're on, so we'll just make it positive, then R equals N minus D. So if we can ever make it to negative, then we'll be good. If we can ever make it to negative, we'll be as close as we can on both sides of the... We'll be as close as we can to 0 on both sides. So ants equals min n mod D, and what would it be? D minus n mod D. Because that's n mod D is how far we can get from the right, and D minus n mod D is how close we can get on the left. And otherwise we can't even pass 0, so there's only one thing we can do, and that's get as close as we can. So that's 2. That's 1. It's 8. 9. What? I have to make exactly k moves. Oh wait, okay. So okay, that is kind of more annoying. How do we do this? I assume that's about this problem. Yes. Okay, so we actually only get one of these, and it depends on rest equals, what is it? N over D. So we get k moves in total, then we takes n over d to get there. If rest mod 2 equals 0, rest equals n mod d. Alright, ants, because we're ending up to the right, because that's how many moves we get to make, else ants equals d minus n mod d. Because rest equals, yeah. So 624, let's say we made it 724. And then 724 because we can get to -1, and then this should be 3. Yep. This is 1. Yeah. So that's correct, right? Because it takes n minus d moves to get as close as you can to 0 from the right, and then for the rest of them. Yeah, okay. I think that works. If not, we'll find out. Let's watch this run. Nice. Nice. Okay. And there are a lot of wrong answers. Alright. Why is that happening? Oh, overflow. Okay. Okay. Why? How do we not overflow? So we want to ask if n minus k times d is less than 0. So we can ask if n is less than k times d, and therefore we can change that to n over d is less than k. Then we won't overflow in that regard. Yeah, I didn't read the constraints in that sense. What? What is it doing? Okay. Actually, must have gotten lucky there with the... Wait, what? N over D is less than K. Why would that be 0? Why would it be 0? I'm actually surprised I managed to pass that enormous sample with this overflow. What are you doing? Oh wait, yeah, n minus d times k. Because now this won't overflow, because that means that m minus d times k is greater than 0, which means it's small. So we can do that. 8. Huge number. 1. Okay, let's test that again, I guess. Alright. So yeah, don't overflow. Read the constraints. Don't make numbers as big as 10 to the 30th. That's good advice that I should follow. Okay, n is small. So we can do some sort of n squared thing. The time limit is slightly larger than usual, which is interesting. Yep. So square I is an integer ci. We just square pi. Wait, what? Oh, the permutation is fixed. Wait. Oh, so we have to do the cycle stuff. Okay, so we will So we can just do this naively, actually. For IM, then we have to make the answer small because it doesn't necessarily have to be 0 if all values are negative. Yeah. For example, what do we have to make? Oh, from 1 to k. Okay. Cycles. I'll do a fancy drawing on MS Paint later about how you can break a permutation down to cycles, and then this whole solution will make sense. Values are small. Yeah, fine. Are they small? Yeah, I guess. Okay, so hello point equals I. Point equals a point. So C size. C val plus equals B point. So if C val is greater than 0, and then cur is the current answer we have. Let's see, cur plus equals, what is it? K over C size times C val. C val is the total value of a cycle, then rem mod equals C size. So then, so then we're going to traverse the cycle one more time. C val equals 0. C best equals max. C best C val. So this should actually be even smaller. Ants equals max ants C best plus cur, I guess. Then at the end, print the answer. Why? Okay, what's with that? Oh wait, this should also be -1, 218, I guess. Although it can actually be smaller than that, but it doesn't really matter. It's -1000. Glad they gave us a huge sample. 295070234469. Okay. Now let's make sure it's all right again. So small answer, small maximum. Do the thing. Do the math. Don't overflow. It will not overflow, I hope. Yeah, it won't. Okay. And alright. Absolute value. Yeah, okay. Great. Another wrong answer. And not many of them, I guess. Why is that happening then? Maybe we misread something. Play a game using a piece of array of squares, number 1 to n. Oh wait. Would it be that? Maybe it would. Well, it shouldn't matter because we would accidentally get that anyway. Okay. So what is with this? Oh, wait. And it shouldn't matter because by default we get back to that anyway. So that should not matter. Okay, so what is with that? Don't know how to test this. 300. I don't know. 1, 2, 3, 5, -6, -7. And then we can see if we get the smallest answer. Okay, now we'll make these positive. Maybe this will be. Oh. Maybe that would do it. Okay, that's very stupid. Yeah. Alright. I mean, is that it? Would that be the only mistake? How many, let's see how many test cases we got wrong. Times 8, so it might have been that. Or the cycle size was divisible by k and it just happened to be the right answer. Okay, let's see if that fixes something. Or if there are even more bugs to behold. Yes, there are more bugs. Cool. Fixed half of them. So what's the other half? Let's so that should be 18 times 33 plus 7 should be 601. Yep. Okay. And that should be 1 38. Indeed. Now this should simply be 6. That's fine. $39. Make it 2. 6, so 5, 7, 13. Alright, why don't we just close it? Okay. Alright, so I don't know what this is. Wait, someone asked why the answer wasn't 7 and then they fixed something else? Well, maybe they were confusing with this. Wait, no, this was actually right. That we move first and then we get the value, but it doesn't make a difference because we can start anywhere on the cycle. We could technically solve this in OVN, but it's not necessary at all. So point equals I. Point equals a point plus whole size zero plus equals the value. Then have the remainder be k, and then if the value of the cycle is greater than 0, otherwise there's no point. I guess there'd be a case where we don't necessarily need to do that. Alright, we're gonna try something stupid, and I think it's going to work because it's annoying. So, if k is greater than or equal to c size, there's gotta be a way to do this problem that doesn't require such annoying casework. I suppose that's what we'll do. Minus 1 rem plus equals k. let's see, so what we want is something like this, where it's 13, negative 15 out of 0. (13, 15, negative 28). Okay, actually this is something that will 7. What? Okay, yeah, so the best thing to do is to do the 28. So if we leave this uncommented, actually the answer here should be 29. Yeah, okay. So that's another case we missed. I think that's it, because we only need to do like one fewer cycle. 8. Alright, this is not going great so far. We're racking up the penalties. Hopefully this passes. I mean, hopefully. No, I don't see why it wouldn't, but at the same time, I don't know why the other ones didn't. Okay. Guess we're gonna do it. Right, it's on the last case. Okay, finally. Alright. That's enough of that problem. Let's just get rid of that code. I don't particularly like it. K items placed on a grid of squares. R times C is small enough. IJ, note the square at the ith row in the jth column. Ith item is at the position has a value. At most 3 for each row. Okay, so I guess it's just that. So we find it. We have 8 bits times 3000 squared times 3. Yep, that's fine in terms of memory. Wait, is it? 9 million. Yeah, okay. So what we're going to do is we're just going to have a value of BP where we have, and this is the number of items we've picked up from the row. So yeah, okay. Then same to n to m to k for each thing. In terms of memory, this isn't anything, so we can just make that one more. Mat r c x. That way we can set that. Okay, hopefully there shouldn't be any stupid wrong answers since there are no special cases for this. I hope. I very much hope. I hope. Come on. Let's do it. So for. So first we're gonna set this to 1e. 1e is 16. That should be a big enough value. Okay, so first, if mat ij is greater than 0, if we have a value, then 4d k3 2 dp I j k plus 1 equals plus the value that we have. So this is what happens when we take this, then dpi plus ij plus 1 k equals max. It's fine that we go a bit out of bounds here because we made the array intentionally too big and we're never going to access the place where we go out of bounds, so it's just like easy implementation. Max dpi j plus 1 k dpi j k and dpi j 0. So this should be the next row because we reset the row counter every time we go down. Wait, we read the problem right? We can only go down and left. Okay. Equals max dpi plus 1 j 0 dpi jk. And that should be it, I hope. Won't doubt that there's still a possibility for us to get wrong answer. What the hell? What? Oh, wait, okay. Yeah. We need a base case here. Yep. So we want to maximize it, which means we make the default value small. That is not right. Okay, why is that? What is that? What? So this would go from 2 down to 0, because that's how my loop works. And this goes from 0 to 3, just for clarity. Which means I am very confused about what's happening here. Why would it be 3? So what should happen is we should have row 0, 1, okay, 0, negative that, negative that, negative that. What? Yeah, 0 indexing, man. That is annoying. Now we'll get 8 as expected. Okay. 0 indexing. What a fun thing to do. And all of the input formats that ever exist use 1 indexing, so we can't do that. Okay, I assume the sample is big and therefore I don't even know. With the luck that we've been having, we're gonna get wrong answer on this. It's a good time to check if we're still recording. Yep. Okay, we got E. It's nice. We have end strings of lowercase English letters. Okay, I thought it was a combo problem for a second. Let's make a string that has a palindrome. Choosing one or more of these strings. Oh. Okay. Okay, I'm gonna go to the bathroom. Be right back. Let's think about this in the meantime. Hey guys. So, general another clarification. What? The answer itself was correct. Okay, that doesn't matter anymore. So, choose A once, which is already a palindrome. Okay, so my general idea is that because these constraints are small, there's not like there aren't. It's like it's not going to be that long. So, is there any sample with -1? Yeah, there is. It's not going to be that long. It's an alarm that I forgot to turn off. Okay. Yeah, I'm not sure where to start with this, to be honest. Let's get rid of all that. First of all, I know string problems are always scary to me. So, let's see. Let's say we did fix the length. For the first string we have, there has to be some other string that's like kind of the opposite of it. How many strings will we actually need to use? So the total length of the strings is like 1,000. Trying to think of some large case. Like, hmm. But then the first sample, the correct answer should be 8. Okay. somehow we have to like bound the input, maybe? Alright, that doesn't make any sense. Maybe we can ask how many times will we use each string. Don't think it's hard to think of an input that will force you to use everything. I wonder if there's anything similar online, because the last, no, not that. Let's check how we're doing. Imagine our penalty is totally dragging us down. Oh, wow. Almost nobody's solved this yet. Okay, in terms of penalty, this isn't actually that bad. We would be, where would we be? We would be around here if not for these mistakes. Okay, this mistake was stupid, so we shouldn't have done that. Alright, I guess it's up to F. Use ABC once and CBA once. So N is big enough that we can't brute force anything, but both the lengths and the number of strings are small. So maybe we do want to fix the length somehow, and then I don't know. Okay, I have somewhat of an idea. Let's say we put one string down. Okay, then. Okay, actually, this actually looks promising. Let's say we put one string down. For example, ABC, AB. Let's use this input. So A, B, C, A, B. I'm also drawing this for myself so I can follow this, right? So now we have 5 of these characters that aren't matched to anything. Now first we want to check if any string itself is a palindrome, because that would be an edge case to this. But let's say furthermore we're having a palindrome that consists of at least 2 strings. Okay, now we have this string, let's say, on the left. It can also be on the right. And we have all 5 of its characters unmatched. So instead of putting another string, which we're going to say is on the left, let's say we're going to attach a new string to the right. So for example, CBA. And then whatever's in here we'll fill in later. So now this matches 3 of these characters. So now we have 2 characters here that are unbalanced. And now that we have this, we can... So because we still have unbalanced characters here, we have to put something to the right again. So let's put another CBA. Then now we have, for this, now this is the longer one. So we have these 2 are balanced, and then we have this character that is unbalanced. But since it's only one character, it's a palindrome. So I think there's some sort of like very weird DP we can do, where it's like DP the string index, like for example, this is string 1, this is string 2, string, and then the side we're on, like left or right, and then the number of characters unbalanced. Then our transition is adding any string, and because we only have to store one string, because once we have this, we're going to put something else to the right. So it's always going to be one string on one side that's unbalanced. And it's always going to be a substring of one of the strings. So let's do this. How are we gonna write this? That's another, okay. So we're gonna dp 51 to 21. Then there's no good way to write this. Maybe we don't need dp. Maybe it's easier to do it like a graph, like Dijkstra, for example. So we can say adding CB, let's say we have ABCAB and then nothing here. Then adding CBA creates an edge from the state of, we're on the 0th string, we're on the left, and we have 5 characters unbalanced, to the state of 0th string, still on the left, 2 characters unbalanced, with cost 4. No, cost 3. Then let's see. Actually, let's one index the strings. That way we can use the state. We can one index the string and the sides. That way we can use the state of 0, 0, 0 as a default. Or we don't have to one index the sides, I guess. Yeah. All right. So let's see. Now what? So we also have a transition of from 0, 0, 2 to, let's say we add a CBA here, then we have, so now this will be unbalanced. So we add an edge. How many states does this leave us with? So we have 2n possible transitions. We have 50 times 20 times 2 states, so it's 2,000. So 2,000 times 100 times 20, because, okay, that's totally fine in terms of complexity. So this will leave us the state with, so now we're at the string with index 1, and then we're still 0 indexing, even though in the implementation we're going to 1 index. So CBA, right. So now this is on the right, and it's unbalanced by 1. So again, any state with this value greater or less than, if this value is 1 or 0, then we're at a palindrome, so we're good. Perfect. Okay, let's try and implement this. This is going to be probably a nightmare, but you know, whatever. Okay, we're gonna use a BPLGs. Actually, what we can do is we can make a Dijkstra thing. Copy in my Dijkstra template. So C into N max x equals what is it? So it's n plus, let's just be 2 to be safe. Or actually, n plus 1, we're going to have exactly that many states times 2 times 21. Times 2 times 21 plus 7, because why not? We don't even need that. Yeah, we don't even need that either, actually. So let's make a Dijkstra, because I have a template for Dijkstra, because that makes it easy. Max. Now, hack. Hello. String number, side, and what is it? What am I doing? Hello, unbalanced. Turn, sternum. Okay. That will work because it's kind of like hashing it. And we will have at most 20 characters unbalanced because like it's only going to be one string. So now for in d dot edge. Oh wait. First of all, string ss50. Then cn, ssi, and ci. And id equals pack I plus 1, 0, side at length, d dot edge 0 to nid. Actually, what we'll do is we'll just, we don't even need that. Let me add the costs. So this will make it both on the left and the right. Then what we do is for in for each string, for each side, we're gonna have to do casework. Okay, what is a good way to implement this? So obviously if it doesn't make a palindrome at all, we can't add an edge. Then okay, let's just do left and right separately. Unval 22. Okay, then once we implement that, the rest is simple. We run the Dijkstra from the node 0, which is the starting state. Then ans equals for in for unval 22 for side 2 pack I plus 1 side unval. Wait, this should only be 21. Yeah. Pack I plus 1 side unval Wait, this should be n plus 2. Because the string numbers are going up to n. They're ranging from 0 to n, so it's going to be n times 2 times 21. So it's going to be max minus 1. N times 2 times 21 plus that times 21. So wait, let's say n is 50. So 50. There's no harm in making this n plus 2, honestly. Let's just be safe. Wait. Okay, that's small. Good. Why did I just say that? Okay. Actually, we only want the unbalanced to be 1 or 2, so that's perfect. Ants equals min ants d dot, what do I call it? Dists id. If ants equals inf. Okay. Oh, sorry, right? So for every terminal state, which is to say we have a 0 or a 1 unbalanced, because that'll make it a palindrome. Wait, for 1r. No, never mind. I plus 1. Okay. D equals pack, I plus 1, left or right, doesn't matter, and the unbalanced. Ants equals min, ants d dot dists id. Yeah, okay. Now we have to do transitions, so we're going to create even more edges, then we're going to run Dijkstra on this graph that we create, and then, yeah. Okay, I kind of like this problem, actually. It's generally a relatively known trick to make some, like, states graph out of something, but I did not find it easy to actually derive the state for this problem, so this was interesting. I'm sure some other reds would be like, whatever, but, you know. Still interesting. Okay, now we have to figure out how to do this. So let's do left first. And then we put a new string down for jn. So we're going to put this string down. So we have okay, so if let's see. Rec equals min. There's no way we need to go anywhere where we're not unbalanced. Okay, wait, actually first what we're going to do is for in, check if any individual string is a palindrome. Bool pal equals 1 for j ssi dot length over 2 if ssi j is not equal to ssi dot length minus j minus 1 pal equals 0. If this is a palindrome, ants equals min ants ci. That handles that special case. Now LOREC equals min min of something. So this is the number of strings we have to check. We're also going to create the new state right now. What is this? So it's minimum of unbalance and ssj.length. That's the number of strings. That's the number of characters we have to check. then hello new stir equals I plus 1 if ssj.length is greater than unbalanced, new stir equals j plus 1. This is the new string that's going to be unbalanced. Side equals 0. Because we're fixing this on the left, side equals 1, and nval equals 0. Now nval equals unval, else unval that's fine. We can do this with an absolute value, but whatever. And then now we just need to check if it's possible. How do we do that? We're going to ask, okay, for 1 hour I, no, k, let's see, rec. So we're going to assume it's possible, then we're going to check all the characters and make sure it checks out. If, let's see, SSI, SSI.length minus unval, start plus k is not equal to SSJ, SSJ.length minus 1 minus k. We're going backwards for j since we're checking if it's a palindrome. Pause equals 0. Let us actually break here. Then it's just 4. Now, if possible, NID equals pack new stir side and val pack I plus 1 what is it, 0 unval d dot edge, and this whole thing is just to add a single edge, NID cj, since we're adding the jth string. Now let's do the same thing but for the right. Okay, so the requirement is the same. Somehow we didn't close this parens. New stir equals I plus 1, side equals 0, side equals 1, then nval. So if the new string is greater length, then we're going to switch sides. Alright, so now we just have to do this. So this is going to be, on the left we're starting from 0, on the right we are that many characters in. So this should be start minus 1 minus k. There's no way this works initially. I mean, I believe in the idea, I think it's right, but there's no way we're gonna make this work. Okay, so see if it compiles. Okay, thanks. And it's because I have to hate typecasting. So no. Does compile. What? Whoa. We're actually passing the samples. 3A50, BB12, CD9. It should be 12, then 3A5, BB12, CD9. Okay, we actually passed the samples. That's kind of scary, actually. So I trust my Dijkstra template to be right, I hope. So let's see, pack looks right. We're not going to have overflow here. We're adding an edge from 0 to that with that cost. 0 to left, 0 to right. Okay. So then we check if anything's a palindrome initially, and that should work. Yep. JN, rec equals min on val, so this is j.length. New string. New string equals j plus 1, side equals 1, so we go to the right. If we switch strings, we go to the right. Otherwise, okay. Now we just check if SSI start plus k, which is the place we're comparing on the left, is the same as the place we're comparing on the right, which is going backwards from k, then we're good. Then if pause, new ID equals pack, new string, side, and val. And then the current ID is I, 0, and unval, and then we add an edge from there to there. We don't want to make it directed, actually. I don't think that makes a difference, but it might, so let's just be safe. Texture works for directed. Should work, right? Yeah, okay. I don't see why it wouldn't. So, same thing, except we just need to make sure we didn't copy-paste wrong. So new string goes I plus 1, side is initially right, and val, so we do the same thing. Set the side to left if we switch. And we're starting from the beginning here, and we're starting start characters from the right for the jth string. Wait, shoot. Okay, this should be... Oh wait, okay, that's actually something we missed. Good. Because the jth string is on the left now, so we need to... Yeah, okay. It's actually concerning that passed samples. That's what we have to do, right? Because jth string is going to be on the right. It might not actually matter, but it might. So let's do it anyway. So the jth string will be on the right, then what we can actually do is unval minus 1 minus k. Because let's say we have 3 characters unbalanced, then it's going to be the first 3 characters. So yeah, that should work. Then same thing, new stir, side, and val. We're making sure we're on the right. Okay. Let's test the samples again. If that broke something, I'd be concerned. 7, 11, 8. And we're going to do something to actually make sure this works. So we're going to take this sample and reverse it. That is ABC, and then BAC, BA, 5, BAC, BA. Then we should still get 11. And we do. Okay, let's try it. Hopefully no TLE. That would suck. Great. Oh, wow. We're actually not that far off, but... what are we missing? What are we missing? should be 10. Okay. So n is 50, right? We have long longs everywhere, I hope. Yeah. Don't actually need this. So it'd be string number times 2 times 21 plus side times 21 plus unbalanced, okay? So into n, max equals n plus 2 times 21. Should be big enough. Read into the string value, then the costs. Then inf equals 10 to the 18th. It's big enough, right? Should be. And dexterous inf is bigger, so it won't change anything. Int equals inf for in, bool pal equals 1. For j, ssi.length over 2. If ssij is not equal to that, palindrome equals 0. And if palindrome, int equals min, ant's ci, because we can already just take one of the strings. This is something weird, like ABA, B, BA. Is this possible? Yeah, it should be 7. Oh, wait, that's just a palindrome itself. Right. It's also a palindrome. How'd you do this, actually? A, B... Won't this be able to just be 10? 9. A, B, A, B, B, A, B, A. Okay, nice. So we do find that. B, 19. Yeah, that part's fine. Stick a C on. Shouldn't make a difference. Yeah. So for I to n, for unbalanced from 2 to 20, what will we be missing here? Oh wait, that's interesting actually. If the remaining thing is a palindrome, then okay, so LL fin state equals pack. We just need anything, like literally any string, 0, 0. Any final state, then so what we need to check is if ssj.length and we need to check if, like, I'll explain this case later. So bool rpal equals 0. So if, okay, now this means that the remaining of that is that. So for I, what is it? Nbow. Oh, we have nbow. Nbow. SSJ I is not equal to SSJ. We can repeat I because my template lets me do that. If SSJ.length is greater than unbow. So here's the case I'm thinking of. So we have like ABAB, CDC, and BABA. 5, 5. Yeah, so that will be caught by this. SSJI, it's up to nbow, right? Because, yeah, we get rid of the first that many characters. Nbow minus ji minus 1, rpal equals 0, else for I nbow if ss, this time it actually matters, if ssi k, no wait, what is it? So it's ssi.length minus nbow plus k, and this will be to the end. So we check the same thing here. So if ssj.length is greater than unbow, then we have some stuff on the left. We're replacing a new thing on the left, so this should be unbow plus I. And otherwise, then we have stuff, yeah. So if SSI k is not equal to SSI nbow minus 1 minus k. What? 10. Good. Let's reverse this. CDC. Okay, let's check again, make sure we got all this indexing right. Let's go. Oh, we got F. Wow, that's kind of clutch. Nice. Alright, let's see where we are. 53rd. Wow, that's pretty good. Yeah, that was quite clutch. This might go down again because, you know, we have a... Wow, we actually don't have that bad of a penalty. I mean, sure, there are some, like... What? Yeah, there's some, I don't know, reds, oranges, whatever, that did crazy good and didn't have any penalties and just thought all these problems were trivial, but... Still proud of this. This is pretty good. Okay, anyway, with 2 minutes to spare, let's start going over solutions, and then we'll see what my rank is at the end. And I guess we can also, rating changes are quick for AtCoder. So this is a new account, so has my handle tied to it, but that's it. So we will get to that. Okay, good time to make sure we're still recording. Let's do this. So A. There's a lot of casework here, to be honest. So A is you're given a string with R's and S's, and you want to find the largest consecutive block of R's. So the string is length 3, which means you can just do whatever you want. Like you can literally like here, one approach you can do is just to try all subarrays and then, or try all starting positions and then see how many R's you get in a row. And then once you get something that isn't an R, break, and then try the next starting position and so on. Another is you can do some like 2-pointer thing. It doesn't really matter because the length of the string is 3. So literally do anything. Let's check the final rank right now. Are we still 53rd? 55th? Okay, it's fine. Yeah. Sweet. That's a good start. Suppose I may put that in the title. We'll have a rule. Any rank that's greater than or equal to 69 we'll put in the title. That sounds fun. Okay, let's do B. So B, we ask... It's kind of a similar problem to the edgy run we just had, but not really. I mean, it's just another triangle problem. So we have a list of sticks, for example, 4, 4, 9, 7, 5, and we want to see how many triples we can make such that there are no, like, for example, we pick 3 indices. How many triples of indices we can pick such that there are no duplicates. For example, these are 2 4s here, so there's a duplicate here, so we can't actually use this. So we use 4 and 7. And that we can make a triangle with these sticks. So the condition to make a triangle is, let's say we were to put 4 and 7 down. Then we were to put 9 down. This is not to scale. I repeat, not to scale. But the idea is, let's write the lengths out in increasing order. So for example, where A is less than B, which is less than C, then we must have that A plus B is greater than C for it to be a triangle. Triangle. Because if it were not, let's say for example we had 4, 7, and 20,000. Right? So we have the measly 4 and 7 sticks, and then there's no way you can ever attach the 20,000 at the end of this. Like, it's going to go off the screen. Right, so if A plus B is less than C, then like you're going to have a situation like this where you're never going to have a triangle. Now let's get a more tame case where we have 4, 7, and 11. Like, the best you can do is a straight line. Because like the lengths are the exact same. You can't actually make a shape. So this is this straight line is called a degenerate triangle, and it's in fact not a triangle, so you can't count it. So all we have to do is check for triples where the two smallest elements are strictly greater than the bigger one, and that they're all distinct. You can do this by a simple implementation is first sorting the array. So you don't have to do this, but it makes it easier. So 4, 4, 5, 7, 9. That way then you can brute force all triples because n is small, n is just 100. So now because it's sorted, you know that the first two elements are the first two things in the triple, then the last element is the biggest one. And at the same time, you know that this element is in the middle. So you only have to compare these two and these two for equality. Since if these two are equal, because this element is between them, it would mean that this is equal to both of them. So you only have to check if these and these are equal. So sorting the array just makes it a bit more convenient, but the ultimate strategy is brute forcing everything. Yeah. Cool, let's do C. C is kind of caseworky. Although not as bad as D. So you're given a number line, let's just draw a line, and you're at some point, and you want to get as close to 0 as possible. In one move, you can either move to the left D units or to the right D units, and you have to make exactly K moves. Oh wait, I'll draw the letter. Exactly. Jesus, that's terrible. Exactly K moves. Okay, so how close can you get to 0? So there are two cases for this problem. First case is that you don't have enough moves to even get close to 0. So for example, let's say K times D is this. Right, like it'll only get you so far. It doesn't even get you close to 0. In that case, like this is the closest you can get to 0. This is the easy case. Otherwise you can pass 0. K times D is passes 0. Then what you'll want to do is, let's say these are the places you can get to and they're D apart. What you'll want to do is, essentially you're just going to jump around between these two. So once you get here, you're going to jump back to here, then you're going to jump back to here, then jump back to here, then jump back to here until you run out of moves, since you have to make exactly K. And essentially that's it. You just have to simulate, well, you can't simulate jumping back and forth, but you can say, you move to the greatest point that's bigger than 0, and then just like take the remaining number of moves you have, mod 2. Then if it's, I'll write out mod. Remaining moves, mod 2. Then if you have one move left, mod 2, you have to jump over here. So then that's the best you can do. If you get to exactly 0, then it turns out it's still the same. Like you'll jump between here and here, for example, or you can jump between here and here. But it turns out that reaching 0 is actually the exact same scenario. So the 2 points would be, let's say you start at n, right? Then the 2 points will be n mod D, because like it's n mod D because it's the, like you decrease by D until you get to a point that's greater than 0. So that's kind of, in a sense, the definition of mod. And then the second point is D minus n mod D. So the first point is m mod D, and the second point is D minus m mod D, and you just do casework to see which one you end up with. However, there's another constraint. There's another issue. K and D are 10 to the 15th. So this movement thing is kd. So k times d can be up to 10 to the 30th. And this is a mistake I made, that you can overflow and you compute k times d. So the condition you want to check is, can you pass 0? And that's equivalent to asking, is n minus k times d less than 0? Now you can manipulate this equation a bit in a way that won't overflow. So for example, you can ask if n is less than k times d. Okay, now you can ask if n over d is less than k. And since we divide here instead of multiply, we're good. And it's okay if we do floor division, that's fine. Since at most we'll be off by 1 if we do floor division, and we're allowed to be off by 1 anyway, since either we'll be here or here. So we can just use floor division to check if n over d is less than k, and this is how we do that without overflowing. So that's essentially the solution for C. Check if you can even reach 0. If you can't, you're done. Otherwise, jump around in these two spots until you do reach 0, or until you run out of moves. Because again, you have to make exactly k moves. That's that. Let's do D. Oh, editorial is that already? Alright, I guess that's not English. So, D is this one. You're doing a permutation. Let's draw out the permutation from the input. So, write that out first. Then we're going to make 2, 4, 5, 1, 3. And to note, these are at indices 1, 2, 3, 4, 5. So you're going, and also each thing has a value. In the sample, for example, it's 3, 4, negative 10. I didn't say example for example this time, so you're welcome. Probably will say it later. In this, so what you're going to do is, here's a number k, another number k, and what you're going to do is you're going to place some chip, some token, whatever, on a position. Then you're going to move it to the position that this permutation tells you to. Here, for example. And then you're going to add the value that's at the position you're at. So for example, 4. That's right? You move it first, then you add it. Yes. So 4, and then here you would go to position 4. So 4 plus negative 8. Then here you go to position 1 plus 3, and then you would make between 1 and k moves. Then you want to make moves to maximize the values you get. Or yeah, you want to maximize moves to make moves to maximize the sum of values you get, where you can make between 1 and k moves. N is 5,000, but k is up to 10 to the 9th, so that's annoying. So, yeah, so the way this works is any permutation can be decomposed into a bunch of cycles. What that means is, for example, 2 will lead you to position 2. Position 2 will lead you to position 4. Position 1 will lead you. Position 4 will lead you to position 1, which leads you to position 2, and you go back and forth. Similarly, 5 and 3 forms a cycle because it just does. Like you can go to 3, go to 5, and go to 3, and go to 3, 5, and go to 3. So you can consider this is called it's essentially called a functional graph, where each vertex has 1 degree. Each vertex, it's a directed graph where each vertex has exactly 1 vertex coming out of it, or exactly 1 edge coming out of it. So yeah. So alone, a functional graph can't necessarily be decomposed into cycles because, for example, this is also a functional graph where you have something like this, something like this, something like this, something like this, and something like this. However, notice that this vertex has 2 edges going into it. But with a permutation, every number appears exactly once. So every vertex must also not only have one edge going out from it, but also one edge going into it. So therefore, this graph is not possible with a permutation. It turns out the only graphs you can have are ones that form a bunch of possibly like disjoint cycles. So for example, this can be a permutation. And then you can have something like this as well. And like this could be a permutation of the numbers 1 to 9, for example. And this could be a permutation of numbers 1 to 3, whatever you want, really. But the point is, any permutation can be decomposed into a set of cycles. That's just a property of permutations. So therefore, now let's go back to the problem at hand. When you place a chip down, like its path is going to be fixed. It's going to move along some cycle, and then it's going to return to the original vertex or the original position, then go back into the cycle and continue moving through the cycle. So we can use that to, in fact, make it so k isn't actually that big, because most of the time we're going to be repeating the same exact cycle. So yeah, so now we have to, okay, I have to figure out how to explain this casework, since as you can see from my my 2 wrong answers, I got this casework wrong. So let me pull this up. Or way to expand this now. Let me pull this up. Okay, so first, I think there are 3 main cases to this problem. So first, let's say the sum of the cycle is negative. This is 3 plus 4 minus 8 equals negative 1. So if you take the cycle, then you're going to be back at the start. You're going to have strictly fewer moves, and you're going to have a negative sum. So there's no reason to ever go back to the start, because it's worse than when you just started off, if the cycle sum is negative. So therefore, if the cycle sum is negative, you're probably going to make fewer than k moves. If the cycle sum is 0, then you might as well not traverse the cycle at all. Like, you might as well not repeat the cycle, because it's just going to be the same thing. And if the cycle sum is positive, you probably want to repeat the cycle a bunch of times, since it'll just give you like infinite, monies, infinite value. Okay, so first, if the cycle sum is negative or the cycle sum is 0, then what you can do is you can just go through the cycle, and for each starting point, for each like position in the cycle, just keep track of the best total sum you have so far. Like, for example, for here you would add 4, and then you go here and have negative 4, and then you go here and have 1. And so the best you would have is 4, so that would be what you take. You also have to make sure that you don't use more than k moves. So for example, as k was 2, we would stop here, and we wouldn't consider this because it's not part of that. This is a 4. I'm sorry for drawing badly. That looks like an A. I don't even know what that number is. Yeah, so we also have to make sure we make fewer than k moves. Now, the real case where it comes when cycle length is positive. So, for example, let's set this to -5. And now, each time we traverse the cycle, we're going to get 3 plus 4 minus 5 equals 2. So we're going to get 2, whatever they call it, score. Yeah. So now what? What do we have to do for this? What we have to do is we have to check some stuff. So there are two possible things we can do. One, the first thing we can do is that we take the cycle as many times as possible. Well, actually, wait, no. Okay, there is actually an easier way to implement this. Let's assume we're going to take the cycle a bunch of times, as many times as we can. But first, let's fix the number of moves the final amount of moves we make after taking the cycle. So for example, we say we're going to move here. So we make one move. Then we have k minus 1 moves left to make, where we can traverse as many cycles as possible. So the number of cycles we can make is k minus 1 divided by cycle length floored. So then, for example, if we decide we're going to make 2 moves, then this would be k minus 2 over cycle length, and we make 2 moves. And if we make 3 moves, then we traverse the whole cycle. Or we can say we're going to make 0 moves, and then it's just k over length. And then, either way, that'd be how it works. So the way to implement this, which is not what I did, because I didn't realize that was an edge case before, is that you will fix the number of moves you make after you make the run of the cycles. And then you'll see how many cycles you have left and add that times like the total cycle value, whatever it is. So for example, 2, because this cycle value is 2. And then you'll add that to the value you get from making the final moves. Plus, we'll say if we do 1 move, it's 4. If we do 2 moves, it's -1. If we do 3 moves, it's 2. If we do 0 moves, it's 0. So that'll be how you implement that. My code does something different. It kind of like it's kind of messy, so I'm not going to explain it really. Like it does the same thing, but like with more casework. So it's not really fun. Let's just move on to E, which was straightforward. It was a nice refresher after getting wrong answers on both C and D. So E is relatively simple. Oh my god, let's see if we can draw a grid this time, or if we're still going to struggle. No, we're still going to struggle. So be it. I think we can take one of the samples here. 2, 5, 5. Okay. I'm just going to steal the samples since they're nice. Okay, we've managed to draw a 2x5 grid. So we're given a 3000. We're given an M by M matrix. Let's say. Oh, it's actually called R by C, so we'll use that. And then wait, let's move this down, and then I don't know why I copy pasted it when I can just drag it down. But so this is E. I'm pretty sure we drew the D. We drew the letter D at the top. Don't demonetize me, please. Okay. And we have an R by C grid. Yeah, so R rows, C columns, obviously, where RC is less than 3000, or less than or equal to 3000, which is cool because that means we can like make a big array and do that. I'm gonna draw that 0. Disgusting R. Still disgusting, but okay. And some of these values. So some of the positions have 0, and some of them have values. So we're gonna steal the sample here. So 2, 5, 5. 1, 1 has a 3. 1, 2 has a 1. 1, 3 has a 4. 1, 4 has a 2. 2, 4 has a 20. And the rest are just zeros. So we're going to start here, and then we're going to go, use a different color, and then we're going to take a path down from the top left to the bottom right. In this path, we can in this, wait, hang on, this doesn't look right. Oh wait, yeah, it is, okay. Yeah, so in this path we can move, for example, we can move only to the right or down. And then moving only right or down, we have to get from the top left to the bottom right. So this is a very well-known problem, I think. And what we want to do is we want to maximize the sum of the values we get in the path. However, actually no, without the however, this would be a very straightforward dynamic programming problem, where we, let's say we're here, either we come from here or we come from here. So let's say we know the best ways to get to these two paths, then the best way to get here is just the maximum of these plus whatever's in this cell. Because these are the two places we can come from, and we've already solved the problem for these two. And of course, we solved the problem for these two by solving the problems for earlier ones, whatever they may be. So this is how the dynamic program would work, and that would be it. However, there's another constraint. In each row, we can only take at most 3 items. So for example, here, we can take the 3, and then we'll say draw it in blue if we don't take it, and then we can take the 4, and then we can take the 2, and then we can go down. So we've taken 3 items for this row, and if we were to take the 1, then we wouldn't be able to take a different one, because we can only take 3. Then we can go here, so now we're on a new row, so we can take the 20, and then we're done. So this would give us a value of 29, which is the optimal answer for this sample, as you can see. So, yeah, as it turns out, it's still a straightforward dynamic programming problem. The only thing you have to add now is that instead of it being dp of row and column, now you have to keep track of a third thing, number of items taken from the row. And since it's, so this can be 0 to r minus 1 if we 0 index. This will be 0 to c minus 1. And this will be 0 to 3, because that's how many we can have taken. We can have taken either 0, 1, 2, or 3 from a row. We can't have taken 4 or anything. So this is RC times 4 memory and also time. So let's see, 3,000 squared times 4 is 36 million, and the memory limit is 1,024, is a whole gigabyte. So like it's a lot. This isn't going to be even close to the memory limit, so that's going to be fine. Time limit is 3 seconds. You know, the constraints are nice. My submission didn't even get close to that, I think. Yeah, it took 300 milliseconds. So I'm sure it's designed to work for other languages if you do it efficiently. So now the transition is, there's one extra transition. So either, now you have a choice. When you go on the path, like you can choose not to take an item if you so desire. So we don't have to take this 1, then we can choose to take the 4, choose to take the 2, choose to take the 20, and be done. Like we're not forced to take the 1, meaning we have to get an answer of 28. Right? Yeah. So, cool. So there are 3 transitions. Let's say you've solved the problem for this. Then you can either move forward here. Or wait, actually no. Let's just let's do normal DP, not feed forward. So I'll write it out. DP R C, and then we'll use K for the number of items taken. Actually, we use T, because why not? It's a nice number. T for taken equals min of min of 3 things. So you can have the array R C plus dp. So this is the transition where you take the item in this row, c t minus 1, where obviously t is greater than 0. And you have to compute this in order of descending t, because otherwise you could accidentally take the same item twice. As you can see, like, you'll compute dprc1 to be 20 plus dprc0, then you'll compute dprc0 to be rc2 to be 20 plus dprc1, and so on. But you don't want to do that. So if you compute in descending order of t, then that's going to be fine. So this is a constraint that t is greater than 0. That, or you could have it, you will come from the previous row. So dp of r minus 1 c, and then something. This something depends on, actually this is kind of special casey. So if t is 0, then you can come from any previous value of t, since it doesn't matter how many you took. Otherwise, if t is 1, otherwise, if t is greater than 0, then you have to have come from something previously on this row, because you have to have taken some number of items from the row. So for this case, if t is 0, you can check all previous values of t from the thing in the above row, since you can have come from any of them. Otherwise, it would be dp r c minus 1 t, and this has no constraint. So if t is greater than 0, then you have to have come from here. If t is equal to 0, you could have come from either this or this, depending on whatever you do. So yeah, this is absolutely amazing handwriting. Ideally, you shouldn't have to rely on this, but so this would be the way to compute it, like basing it off of previous values. What I did was I did like feed forward dp, where I use the value I'm currently at, and I kind of like push it onto the later values. Yeah, so this is where I take the item and then I say this state gets better. And then and then when I'm at here, I say the next state is going to have the minimum of its value and this, and the next state here is going to have the same thing. We can also do it this way. And the transitions, of course, are either you take the item and then you've taken the item, or you come from somewhere previous. Now, if my handwriting is unclear, I guess you can ask about it, but it's also a good idea to just try and work this out for yourself. This is an R, by the way, and this is a C minus 1. So, yeah. That is E. You just do dp, and it's relatively classic. Now F. I liked F. This was nice. This is actually a good like AtCoder style kind of problem where you have to like pull out some random solution out of nowhere. I like these types of things. So what you gotta do is you're given a bunch of strings. Let's say B A, A B C, and C B A A. Okay. Now, and each string has a cost associated with it. Let's draw F, and then move these down. Each string has a cost associated with it. In the sample, this is 3, this is 4, and this is 5. What you're going to do is you're going to arrange the strings you're going to take some string and just like plop it down. And then the cost of plopping it down is, of course, its own cost. And then you're going to plop the strings down in some order so that they form a palindrome. You can use each string as many times as you want. So for example, you can have BA, BA, BA onto infinity if you like, but it's not going to be a palindrome, so I don't know why you would do that. And so for example, this would be one order of plopping things down you can do, and this would be 3. So the total cost of this would be 7, and it would form a palindrome. Another thing you can do is, for example, A, B, C with 4. Then I'm just going to draw everything in the same color. CBAA with 5. This actually isn't a palindrome, but that is not an A. What the hell did I just draw? Yeah. But what you can instead do is you can make it like in any order you want. So you can do CBAA and then ABC. And this would be 5, this would be 4. This is a palindrome, and that would be 9. So you want to find the minimum cost that you can spend to make a palindrome. And sometimes it may not be possible. For example, if you have like one string that's like, I don't know, AZ, it doesn't matter what the cost is, you can't make a palindrome with that. So sometimes it's not possible, you also have to check that. And how would you do this? How would you do this indeed? So, first thing to notice, the constraints are tiny. Like n is 50, the length of the strings is 20. So there's probably some, like, I don't know, some sort of dynamic programming thing. N is 50, which means it's too big to brute force things, especially with the lengths of the strings being long. So there's no way you can, like, try all permutations or try all configurations or something. Or, like, do a prune to brute force. I don't know. Anyway, that's not intended, and it probably won't pass. So that's not the route to go. Instead, you can do something smarter. So small constraints generally tend to scream some sort of like DP solution. But how do you even do that? Because like the states are strings. There are a lot of states. If you consider each character, then there can be a lot of states, and that's not good. So you have to, in a sense, the thought process should be you have to reduce the state space somehow. You have to find a way to represent all the information you need in a way that's not going to be, say, exponential. And it turns out there is a way if we pick a smart order of placing down the strings. What is this smart order, you may ask, because it's the solution to the problem. Well, let's say you plop down ABC. Okay, now we declare that this is going to be on the left, which means that we have to have some like magic dust on the right, some strings that like match this. Maybe there's more stuff on the left, I don't know, like we can stick a CBAA here, but we still have to have all this stuff on the right. Add some more colors in. I'm an artist. Yeah. So what this means is now, like, we're asking for the stuff on the left to be balanced by something else from the right. These 3 characters are unbalanced, we'll say. So yeah, how will we do this? So now, since these 3 characters are unbalanced, we want to place something on the right. So for example, let's say we place CBAA. Now these don't match. Like AB doesn't match with AA. I should draw it like this. So A matches with A fine, but B doesn't match with A. B doesn't match with this A, so we can't use it to match the palindrome, and of course C doesn't match with B. So what we can instead do is, we'll say if we have some unbalanced stuff on the left, then the next string we place, we're going to say is on the right. And then, so for example, we'll put BA down, and then now these 2 characters become balanced because this matches with this and that matches with that. So now we have one unbalanced character on the left. So now we want to balance that. Well, actually, here we're done, because if we have 0 or 1 unbalanced characters, then we just have a palindrome. But otherwise, let's say we want to put something else down. So let's say we put down ABC. So then this matches with this. So this works. So now we're done with this, and we're done with this. But now we have an unbalanced string on the right. So now we're unbalanced on the right by 2 characters. So now we have to place more strings down on the left, and so on. But notice that we don't really care what the actual characters are. Now we only care about how unbalanced we are. And since as soon as the unbalance changes from the left to the right, for example, then we're going to start putting stuff on the left. So it's going to be only some part of a single one of the input strings that are going to be unbalanced. So therefore, we can represent the state as the input string that's unbalanced. Also, if we're on the left or the right, because that matters, and the number of characters that are unbalanced. This is our state. That's it. We've reduced it to this. Now there is a single special case here. For example, if you have the strings A, B, C, D, C, and B, A, right? So if we place down A, B, C, D, C, then we have 5 characters that are unbalanced. So we place down B, A to balance it. Right, so then these are going to be balanced, but this remaining string is a palindrome by itself, so we're actually done. So the way to handle this special case is, the cool thing about this special case is that since it's a palindrome already, it's 0 cost to do anything else, and that's it. You can check it because it's still a state. It's still a string. It's still a certain number of unbalanced characters on a single side of an input string. So we can check which states instantly lead to being done. That's a nice way to handle it, actually, yeah. So we can check which states instantly lead to having a palindrome. And then we can say once we get to any one of these states, then we're done. So a state leads to having a palindrome if the remaining unbalanced characters are themselves a palindrome. This could be if they're of... Let me get some water. This would be if they're of length 0, if they're of length 1, or if they form a palindrome at the end. And of course, being of length 0 or 1 implies that there's a palindrome, so that's good. My code handles these 2 cases, the 0 and 1, and being a palindrome separately. However, you can do them however you want. You just have to make sure that you keep track of all the states that are end states. They're at the end. So then, say you get the minimal cost to go to each of these states, then the answer is just the minimum value of all of the end states. And if you can't ever reach an end state, then you're just done. So you can also, this actually also applies nicely to checking input strings that are palindromes themselves. All right, if you can't get to an end state, there's no answer, and you'll just print -1. So for example, if this string is a palindrome, then both of its states, say for example, this is string 4, its side is 0 or 1, it doesn't matter, and the number of unbalanced characters is its length. Because this is a palindrome, it's already an end state. So that's also something you can check. Or you can just be safe and check at the beginning if each input string is a palindrome, and if so, check the answer with its cost. let's say for example this is 9, then you still want to do the rest of the algorithm because, like, for example, ABC plus BA has cost 7 and it's a palindrome and it's better than 9. One of the samples actually covers this, that you have a string A, however it's better to use AB and CBA to make a palindrome because it's cheaper. Yeah. So now we just have to figure out the minimum cost to get to all of the end states. And the way we can do this is we can basically make a graph out of these states. What you can do is you can compress, like, these are just numbers, because this is an index of a string. This is a 0 or 1 for left or right, and this is a count of unbalanced characters. You can compress all of this into a number. Like, for example, the number of unbalanced characters is at most 20. So it's like basically, and the number of sides is at most 2. So you can kind of hash this this 3-tuple into something like index times 2 times 21, and then this, you'd multiply the side by 21, and then you'd multiply this by 1, and it's kind of like the idea of polynomial hashing, or to put it in a simpler way, how would you put it in a simpler way? It's like you create a base 21 number out of these 3 numbers, except this is like just 2. Doesn't really matter the way you think about it. You just need to figure out, and you don't even need to do this compression actually, as long as you have some like Dijkstra that will let you do this. So, I mean, that's fine. You can either compress it to an integer or not. The way my thing works is that because this is at most 20, like, if you have 21 times the side, you'll be able to floor divide by 21, and then you'll be able to get the side. Because no matter what, the unbalanced characters isn't going to affect the value that the side contributes. Because this is 0 to 20, then this is either 0 or 21, and then this is multiples of 42. I am not explaining this well. Anyway, compressing the state is the least important part of the algorithm, so don't worry about that if you don't understand it. You can just use like a 3D array or something, like vector, or whatever language you use, vector, I don't know, something, edge. E, and then like, I don't know, you can make it 50 strings, then 2, then 21. Or you could just do whatever you want, really. You can make it at the same time 2100, since that's the biggest it could be. And it might be 2150, depending on how you do it. What I did was I one-indexed the strings. That way I can use 0, 0, 0 as the initial state. But anyway, this is all just like, this is all implementation. We still need to figure out how to, like, the minimum way to get to each state. And the answer is very simple. It's just Dijkstra. You're asking for the shortest path from the initial state 0, 0, 0. And we'll write an index. This is index 1, this is index 2, this is index 3. You're asking for the shortest path from the initial state 0, 0, 0 to any of the final states. Of course, if you can't get to any final states, it's -1. Otherwise, you look at all the final states and you just ask, like, what's the shortest one? And of course, computing the transitions is also not easy. You fix one transition, and then the transition to another state is like adding a string on whatever side that this isn't. Whatever side that this isn't, and then you can compute the new state it gets to, and then you would add an edge with a cost of whatever the string you just added is. And then you would run Dijkstra's from 0, 0, 0, take the minimum over all final states, and that would be your answer. Yeah, that was it. I'm going to that like whole session of rambling, I'm going to cut it out. I won't edit it since it could possibly be useful for implementation, but I'll just I'll put in a separate timestamp so you won't have to see all that if you don't want to. Yeah, that is F. Okay, let's check the standings now. So my rank shouldn't have changed because there aren't system tests, but sweet. So now we have rating changes. And yeah. Oh, where were we among rated participants? 13th, nice. So do I put rank 13th or rank... No, I guess it would be rank 55. Anyway, this was AtCoder Beginner Contest 175. I enjoyed some of the problems. Maybe not the last one, but... Or, no, I liked F. Maybe not C. D had a nicer implementation than what I figured out, so... Once again, just like the edgy round, I overcomplicated the implementation. Yeah, sometimes it's a good idea to just... Like, if you have a solution and it seems ugly, just take a minute to try and think of something better. If you have a lot of time, of course. If you're, like, low on the clock, don't. But just take a minute or two to see if you can come up with anything that's easier to implement, because it's going to make it easier for you in the long run. Yeah, that's my advice. I guess that's it. Get the 2400 performance, because that's the cap. And we'll be off. Hope you enjoyed.